So, well, thanks again for coming, for joining. And today we will continue with the study of low energy effective field theories. But today I will explain you the way to package all the soft theorems and constraints on the low energy couplings of Goldstone bosons into an effective Lagrangian, which is the modern way that people understand low energy physics. So before that, let me first open my laptop because I have to read something for you in a moment. Okay, so it's ready. Okay. Okay, so today we will discuss effective field theories, pions, and non-linearly realized symmetries. And let me remind you the points that we discussed last time. So there were 4 main points, which are basically point A. We can use the effective potential to get the feeling of what is the vacuum structure of the theory in the IR. And as we discussed last time, we can just plug constant fields into the potential, into the bare potential to get a 3-level picture of what is going on. So for instance, in the Mexican hat case, we could see that, okay, there are 2 minima, and if there is some additional symmetry that allow you to rotate this potential in this way, then you see that the minimum is not invariant under transformations. And this is what led us to the second point of the last lecture, which is that if the vacuum, so this is phi bar, this is phi, this is the potential. So if the vacuum is not invariant, then we have Goldstone bosons. And we have as many Goldstone bosons as number of broken generators. Then we discussed a little bit more in detail the interaction between Goldstone bosons. And for instance, we related, of course, we showed that the vacuum expectation value of the scalar that breaks spontaneously the symmetry, which I will call the V with the VEV, which is the VEV, usually it's called VEV, is related to the spectral density. So we show that rho mu squared is a delta function at mu square equal to 0, which means there are only massless particles in this spectral density. And then we also showed that we could, for instance, if we parameterize these matrix elements, which were we used to decompose the spectral density last time. So for instance, vacuum, current, Goldstone boson state, and then Goldstone boson state, field that breaks the symmetry vacuum. And we parameterize this with F, P mu, and then some normalization factor which are not important, and Z times normalization divided by normalization factor that are not important. We could relate basically the VEV to this coefficient F and the normalization, basically the residue here Z. Now, what is F? F is the price that you pay to emit Goldstone boson. Okay, so we would expect that if we define a Lagrangian, as we will do in a moment, the coupling let's say the coupling cost of this Lagrangian will be related to this F. Okay, that suppresses the interaction. And then the last thing that we said is that these are only consequences of nonlinear on spontaneous symmetry breaking on 2-point functions, but there are infinite relations. For instance, we just mentioned, because it's like a bit lengthy to prove, but we just mentioned that if we three derivatives of the effective potential, this we mentioned at the end, with quotation mark, because we have to sum over generators and so on, but morally this is equal to 0. This means that Goldstones do not have trilinear coupling. And this this relation among 3-point functions implies that scattering amplitude or 4-point function vanish when you take one of the legs soft. So this was like crucial to prove that if we consider a scattering amplitude with P1, P2, state, P3, P4, and we send one of the Pi to 0, this we expect to be 0. Okay? So it took us one lecture yesterday to get to this point. And today, what I will do is that I will explain you the formalism that allows you to package all this information at once in one effective Lagrangian. And that's the idea of effective field theories. So today we are going to discuss the effective field theory approach. Field theory approach. And I remind you again with this picture that we use this approach when we are not able to follow the RG flow all the way to the IR, where we cannot make computations. So for instance, in QCD, we know there will be some CFT in the UV that is deformed by marginally irrelevant deformations. So there will be some deformations and so on that make material flow into the IR. And then in the IR, the only thing is that we have these goldstone bosons. And this is extremely hard to solve. Like people use lattice field theory to solve this. So the effective field theory apply in this regime in which basically you write Lagrangian, writing all possible terms that are compatible with the symmetries, and then all these terms are weighted by powers of energy. So the more terms we add, the more we can climb up in energy. So we will see that there will be some leading Lagrangian that describes the very low energy interaction between the goldstone. Then as we add interactions, we will be able to climb up the flow a little bit. Okay? And if we add infinite interaction, we would be able to shoot up and go to some UV. But you see that, of course, the flow is not reversible, the RG flow, right? So we can go up, and we can go up in many different ways. They will correspond to all possible UV completions. Right? So this is the idea. Yes. Sorry? No. No. Unfortunately, it's too far. Okay. So before doing this, I will basically read from this very beautiful paper by Weinberg, which is this effective Lagrangian paper, which has this statement, which is really at the core, I think it's like the core of the effective field theory. So basically, he's saying something about that it's very hard to justify all these properties using current algebra, using commutators between currents, that like we did last time. And then he says, this remark is based on a theorem which is, as far as I know, has never been proven, but which I cannot imagine could be wrong. The theorem says that although individual quantum field theories have, of course, a good deal of content, quantum field theory itself has no content beyond analyticity, unitarity, cluster decomposition, and symmetry. This can be put more precisely in the context of perturbation theory, and if one writes down the most general possible Lagrangian, including all terms consistent with the assumed symmetry principles, and then calculates matrix elements with this Lagrangian to any given order in perturbation theory, the result will simply be the most general possible S matrix, consistent with all analyticity, perturbative unitarity, cluster decomposition, and symmetry principles. As I said, this has not been proved, but any counterexamples would be of great interest, and I do not know of any. So this is basically the statement. So Weinberg basically was saying back in the days that we can just guess the result of any quantum field theory computation based on the general principle of crossing symmetry, unitarity, and analyticity. And that will be the most general results. And then how we parameterize the result in detail will depend on the details of the UV completion. All right? Okay. Yeah, 1979. So it's basically the bootstrap. Okay, so let me start. So what we will discuss, so just to remind the notation I'm using, so we will study pions. So we will really focus on this symmetry breaking pattern, SO4 that goes to SO3. And what we will show soon is that the effective Lagrangian is built out of a covariant derivative, the mu pi, which is just the usual derivative dressed with an appropriate function, which in this case, it can be this function here. So basically, the recipe to construct an effective field theory for a Goldstone that spontaneously breaks this, that appear because of this spontaneous symmetry breaking, will be to write a Lagrangian in terms of these covariant derivatives. And then the most general Lagrangian will just be something like coupling G2 times d mu pi plus dot dot dot. So the goal of this lecture, it will be one, to explain why we need d mu pi and not something simpler than that. And the second point will be to show how a Lagrangian that is written in this way, admits a well-defined perturbative expansion. In the coupling that will be not sub-Berg coupling, but will be the energy scale. Okay, because it's like a derivative interaction. So we will show why this gives a well-controlled expansion. Okay, so are there any questions so far? Yeah, please. I will tell you in a second. Yeah, thanks. Okay. Okay. Now, just to answer the question, I will tell you why SO4 and SO3, and the reason is that we are studying pions. Okay, so now we talk a little bit about pions. Sorry? Yeah. Yeah, I will start from there, yeah, from the UV theory. Sorry. Sorry? Ah, well, okay, yeah, sorry. SO4, I really mean just SU2 times SU2. That is broken to SU2, which is SO3. This is what I mean. Yeah, just at the level of the algebra, not the global group. Yeah, of course. Yeah, it's like a, yeah, it's just Lagrangian, so just the algebra is enough. Okay. So the UV Lagrange. So to explain what I mean by these relations, the UV Lagrangian, we know it will contain some up quark field with the appropriate covariant derivative, Dirac operator like this, and then d bar, gamma mu d mu d. And then there will be dot dot dot, but this dot 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 correspond to mass terms. And since up and down quarks are very small, I can set this mass term to 0 for simplicity. Okay, so I will work in this limit. Now, this Lagrangian is invariant to various transformations. In particular, is invariant to UD that goes to exponential of, there will be an I, there will be a factor 2, and then there are two terms. There will be a simple Pauli matrix with some vector theta that I call theta v. And then there will be a second term with, again, the Pauli matrix, but now there is a gamma 5 matrix, okay, because of the spinor indices. And this will be theta A, acting on UD. So it's easy to verify that this is indeed the symmetry of this Lagrangian. And now let me make a comment, which is actually this Lagrange is invariant under more symmetry than this. Actually, it's like U2. I'll show you in a second why it's SU2 times SU2, but it's U2 times U2. And this corresponds to a global rotation of both up and down fields. So if I rotate both up and down quarks by a simple phase, this corresponds to what is called the baryon conservation number, which is an accidental symmetry of the standard model. We don't know any violations of this. And then there will be another symmetry, which is e to the alpha times a gamma 5, with an alpha that acts on both up and down quarks. And this is broken. And this is anomalous. This is broken by anomalies. Okay? This is broken. So I will just restrict to this SU2 times SU2, not bothering about these actually important issues. Okay. And now to see why it's an SU2 times SU2, let me remind you that it's always possible to diagonalize this symmetry, block diagonalize this symmetry by introducing generator T left, which is just 1 minus gamma 5 divided by 2 times sigma, and then T right, which is just 1 plus gamma 5 divided by 2 times Pauli matrix. And then you see that, of course, if we sum T left plus T right, we get this part of the transformation. And if we subtract, we get what is called the chiral, we'll call it X, what is called the chiral part of this transformation. Okay, is this one. Now you see this left and right, well, by summing left and right, you see that T is even under parity, and X is odd under parity. Sorry, this is left, this is left. Okay, so this will be even, and this will be odd under parity. And now, if we look at the symmetry algebra in terms of this T left and T right, it's basically immediate to show that T left times T left transform like an epsilon times T left. Right is the same thing. And then T left commutator T right is equal to 0 because 1 minus gamma 5, 1 plus gamma 5 are two projectors. Okay, so when we mix them together, these products are 0. And in this way, it's clear that this transformation can be written in terms of SU2 left times SU2 right. Okay, so this is like, but now there is the experimental fact. So what is the experimental fact? That nature likes not these transformations, but likes more this, and it will preserve only one of these two subgroups. So let me erase. Yes. Yeah, flavor. Yeah. Okay. So in terms of T, so let me just write in terms of T. So in terms of T, so this is like even times even, it will give me some epsilon T even. Then when I rotate T and X, I will get, so what I mean by this, of course, is just mean this is A, this is B, there will be an I, and this will be epsilon A, B, C, T, C. Okay, so let me just be a little bit schematic sometimes. So Tx, here we will have like an epsilon and we will have X, because it's odd. And then when we take commutator X and X, we will get, this is odd, we'll get something even, so we'll get T again. Okay? Now, these generators, actually, we can also write currents out of the UV Lagrange. So what are the currents associated to this symmetry algebra? So there will be what is called the vector current. So just let me write it for completeness. that will be I Q bar gamma mu Q. And then there will be the axial current, which is associated to this X. And they'll be given by Q bar gamma mu gamma phi Q. And as I reminded you last time, the charges that that makes the field rotate are constructed out of these currents by integrating. So there will be some big T, which is d3x v0 x t integrated over space, and there will be like a big X, which is the chiral charge, integrating the 3x of the component 0 of this pseudo vector current. And oh, thanks. Yeah, they have like flavor index. Okay. Now, of course, this charge, they will rotate the field. So we have TQ, it will just give me minus TQ, okay, where those are those Pauli matrices, and X acting on the quark field will give me minus X Q. Now, if this symmetry were exact, let's say, then it would mean that for any hadron state, you see, let's imagine that we take an hadron state with positive parity. Then when we add with this charge here, X, we would get a rotated hadron state, but since it's symmetry, it will have the same mass. But since this operator has odd parity, this state will have odd parity. So it would mean that when we look at the spectrum of the theory, we would observe particles that have the same mass, but opposite parity. And since this is not happening, since we observe only one parity, one parity possibility, basically, one of these subgroups should be broken. And now, experimentally, what happens is that this is unbroken, and this is what people call isospin symmetry. And this part will be the broken one. So this part will generate Goldstone bosons. So we expect massless particles in the spectrum. And with which parity? Well, the quantum numbers of the Goldstone boson are related to this charge, right? Because now we expect that when we act with this operator E, with the charge X on some state H, we'll get H plus a Goldstone boson. So it has the same quantum numbers as this component A0 of the current. So it will be spin zero particles with negative parity. So it will be pseudoscalars. And indeed, what we observe in QCD is that we observe the lightest states in the theory are pseudoscalar particles. Okay. And how many of them? So let's do the count we did last time. So this, in terms of algebra, we can think that we have this breaking, SO4 to SO3. And as we did last time, we expect 4 times 3 divided by 2 minus the number of unbroken generators, which is 3 times 2 divided by 2, just counting the number of independent components in this group. And what you get is 3. And this is exactly what you observe. So we are sure that this is a very good approximation of nature. Okay, so this explains, I think, your question why SO4 to SO3 is what we want to do. Okay. So, any question at this point? Yeah. Yeah. Sorry? Well, it's very schematic. I'm just saying that since we have the, as we explained last time, when you have like a spontaneous symmetry breaking, what you expect is that the symmetry does not, does not less state invariant or, right? You produce a state with the same mass, but emits Goldstone bosons, basically. Okay. Mm, yes. Yes. So so I'm thinking about usual strong interaction. So CP is conserved, right? So I will not really I will not couple it to electromagnetic currents. I will not care about the charge. So for me, it's just they have like negative parity at this point. Pseudo because they are scalar but with negative parity. That's the usual. It's like how people were calling these states. Yeah. Well, okay. So let me say it that when no, this does not break anything because when you couple it to the currents, you will get state with any charge. So like pi plus, pi with charge plus, minus, neutral. So there is no, like CP is conserved by strong interactions. There will be no break, even if I couple to electromagnetic charge. But, no, but this is a nomenclature that comes from the 70s. People in the 70s, if something is scalar, it's not parity plus, it's weird. So that's a little bit where the name comes from. No, no, no. So, yeah, so the state has like negative parity, the interaction does not break anything. Yeah. 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 Well, yeah, scalars, yeah. Yeah. This vector here is because of this isospin, it's this isospin symmetry. So 0 was the temporal component of the vector. Yeah, well, maybe another thing that I should have said, these are 3 because they are in the representation with isospin equals to 1. Like SU2 group, so it's like spin equals to 1. There are 3 components. Like this current, same quantum numbers. Okay, so very good. Now let's go to, well, so we explained why we are studying this symmetry breaking pattern. Now let's go to explain why we need to use this covariant derivative, which is really the gist of the effective field theory. So maybe I can erase this part. We will not need, we will not need this anymore. Maybe let me erase this part here. Okay. So we will start with what is called the linear approach. So there are many different ways to derive this result, but let me start what is called the linear approach. And in the linear approach, we really start with some model. So we start with some Lagrangian, which will contain, for instance, a Lagrangian which is SO4 invariant, which will have, of course, a kinetic term, d phi square, and then there will be some potential which only depend on phi square. Okay, and this phi, it has like 4 components, phi 1 to phi 4. And this is manifestly SO4 invariant. And now we have in mind this picture. So we have in mind this picture in which the bare potential, it has a degenerate set of vacua. So we have some symmetry here. that allows us to go around this Mexican hat. And we pick one direction, right? So now let's imagine that we pick one direction. And we call this phi 0, which is 0, 0, 0 sigma. And now we decide to parameterize the generic field phi in terms of this starting point. So the generic field phi will be equal, so phi of x will be equal to some matrix R, which depends on x, times phi 0, which in component looks like that phi n of x will be equal to R n4, component n4 of x, times sigma. It's just a nonlinear change of variable. So it's like my choice of parameterizing the fields. And now, something that you should, that we would already expect based on simple consideration is that if we consider a constant R, so a matrix that does not depend on X, then this is actually a symmetry, right? Because it just rotates this vector that we choose to parameterize the vacuum direction, but it's not important. So we would expect that constant rotation do not cost any energy, so they do not enter into the Lagrangian. So therefore, we would expect that this Lagrangian, it has to be derivatively coupled in this rotation matrices R. So let's do this change of variable. So if we do this change of variable, we see that there will be some minus 1/2 d sigma squared, so some term for d sigma. The potential will only depend on sigma squared, and I will tell you in a second, I will remind you why. And then there will be a term which is of course proportional to sigma squared divided by 2, but then there is this sum over n to 1 to 4 d mu r and 4 d mu r and 4. With the condition, of course, that this R is a rotation matrix. So it's an SO4 rotation matrix, right? Because this Lagrange is invariant under SO4. So this R field, it's a rotation matrix. And in particular, since it's a rotation matrix, we know that R times R transpose has to be equal to 1. And then we know that if we take a derivative of R times R transpose, this is equal to 0. And if I write it in component, this tells you that sum over n equals to 1 to 4 of R and 4 square must be equal to 1. And then sum over n equals to 1 to 4 of d mu Rn4 times Rn4. This has to be equal to 0 as a constant. Okay, so this is what is called nonlinear sigma model. So it's a model where the Lagrangian has fields that are constrained nonlinearly by this relation. It has to be some normalized unit vector. Okay? And basically, if you want to show that from this, plug in this relation, you get this Lagrangian, you need to use both these two properties. That the sum of this rotation square is equal to 1, and then if we take this derivative, this vanishes. Okay. So now, you see, the sigma field will have no importance in the discussion, because in particular, if the sigma field has some mass, let's say we can just freeze it, because it will be some gapped excitation that we don't care. We only want to describe the dynamics of these fields R, and this will be identified with the Goldstone bosons, of course, because are the massless fields in this Lagrange. All right? So let's say that, for instance, I could call R and 4 with n to 1 to 3. These are my pions. This is what I could say. And then I could say that, of course, R44, it's just square root of 1 minus sum over n from 1 to 3 of R and 4 square. That you see that it's constrained. Okay. But this is one possible choice. There are infinite choices, right? Because we know that there is field definition, and the theory in general is like it's invariant under field definitions. So let me use the parameterization that then it's also used by Weinberg, in which instead of using this R, we will use this field pi, and this will be really the pions. So instead of this R, we use Rn4 is equal to 2 pi n divided by 1 plus pi squared. And then R44 is just 1 minus pi squared divided by 1 plus pi squared. And now it's like an exercise, some gymnastic actually, to show that indeed this parameterization automatically satisfies this constraint. And okay, and then something that also you can show that it's again some algebraic exercise, that the Lagrangian, once I introduce this field, can be actually written as L sigma minus sigma squared divided by 2 times d mu pi square, where d mu pi square is the one that I defined there and that I erased before. So d mu pi square, if you use this parameterization, it turns out to be d mu pi, let me write it again, divided 1 plus pi square. Okay, so this is like a result of an explicit computation. Okay. Now, let's understand, using this Lagrangian, let's understand how the symmetry is non-linearly realized. So what happens now to the various symmetries? Okay? So, first, let's notice the following, that if we basically act 2 pi with some rotation r of SO3 that leaves this vector invariant, so the rotations orthogonal to this direction that we picked, this automatically leaves this Lagrangian invariant, okay, because it depends just on pi square, where the vector indices are contracted. So this is okay. And in particular, we see also why sigma is not important, because sigma does not enter into any symmetry relation. Delta sigma, if we perform this transformation, just equal to 0, and then delta pi, it's just epsilon vector pi. Okay, it's just like as a vector should rotate. Right, so this is clear, right? The variation of vector, a variate vector, and the small variation just orthogonal to the vector itself. Okay, so this is the linear part, and this is what we would expect, because this is the unbroken part. And now what about the broken part? Well, the broken part is more complicated, because you see, in the original Lagrangian, it's pretty obvious, because the broken part just rotates this direction here. So it's just a rotation of this phi. And in a rotation of this phi, of course, I can parameterize it as delta phi 4, which will be basically some, let's say, I use again epsilon. So let me call this theta. I like to use epsilon here. So I will basically vary this field phi into some orthogonal direction. So this will be like phi 1, phi 2, phi 3. And then delta phi, it would be just plus 2 epsilon times phi 4. So this is like immediate to show that it leaves this Lagrangian invariant. And this is transformation that rotates the vacuum direction. Now, if we write this relation in terms of these fields here, pi, it's obvious that will be very nonlinear. And indeed, what happens is that delta sigma, again, is equal to 0, so we really don't care about this delta sigma. And delta pi, it will be epsilon 1 minus pi squared plus 2 pi epsilon dot pi. Hmm? Now, you see, the beautiful thing is that we started from a Lagrangian, which is manifestly SO4 invariant, where the symmetry acts linearly on the field, and we obtained a Lagrangian in which only the unbroken part acts linearly, and the broken part acts non-linearly. And actually, now you can also understand why we obtained all these relations involving multi-point doublet, right? Why we obtained the soft theorems, so relation between 3-point function, 4-point function, 2-point function, and so on. Because this variation of the pi field is nonlinear. So it will generate word identities that involve different number of pion fields. So it really comes from this simple fact, all these soft theorems. Okay? Any questions so far?
Epsilons on the right-hand side, are they SO4 or SO3?
This one? SO3, yeah. Yeah, it acts on this phi with the vector. Yeah, maybe I used too many vectors. Here at the beginning was a 4 vector, now it's 3 vector. So let me remove it from here. Yeah.
We're supposed to be showing how the SO4, that's the broke, so SO3 is the unbroken.
So this SO3 is the unbroken part, because these are the rotations which are orthogonal to the direction that we picked at the beginning. While this rotation, it rotates the direction 4, which is the one that we choose to as a reference frame, basically. And the original Lagrangian must be invariant, does not depend on this choice that we picked to parameterize our Lagrangian, and therefore, in this language, it's linear, but then when you express in these coordinates, it becomes very nonlinear.
Yeah, but those generators have to be different.
Which generators?
Right, the ones in the epsilons in the right of the.
Yes. I called it theta. Yeah. No, it's different. Yeah, that's why I said before it's epsilon theta, I will call it theta. Okay.
By the way, so this is all concerns about local argument. So precisely as you do that state of fall, not the fall.
Yes.
And the broken down stuff is actually factor for the scale 3.
Mm-hmm. Mm-hmm.
So are you aware of the implications of that for the local factor beyond the low energy? Okay, so are you aware
No, the only thing that comes to mind is related to instantons and so on, but here I'm not. Yeah, I'm not an expert, so now I forgot. But here I will not discuss instantons because I'm talking about low energy effective field theory, so yeah, it will not be important for this discussion. Yeah, no, but I'm not the right person to open this door, maybe, you know. No, thanks for the comment. It's very good. I mean, yeah. I can tell you something else. I mean, why, for instance, why we know that there are no colored states in QCD? Because, for instance, global colored states really depends on how we integrate the gauge group at infinity. Right? So this also will depend on the topology of the gauge group, and that's something that we don't know. Right? If the gauge group at infinity goes to a constant, or we should integrate also at infinity. So then there can be like colored states in QCD, which are gauge invariant, but global colored, for instance. So, you know, there are many subtleties, but, you know, if we start to discuss these things, we never end. No, I mean, I'm thinking about like what, so you asked about these global properties, what are the implications of these global properties? An example is the existence of colored states in QCD. the question why you don't have global colored states which are gauge invariant. And it's not clear, it's an experimental fact. And it really depends on how you choose to integrate over the gauge group. Because if you integrate with the gauge group that at infinity acts non-trivially, so does not go to a constant, but goes to some gauge transformation, then you wash out all the colored states, right? Because you just obtain singlets. But instead, if the boundary conditions at infinity are such that the gauge field goes to a constant and you do not integrate over, then you can have colored states. That would be like one of the implications of these global properties of groups. Okay. So now let me make another comment. So something that we have to convince ourselves that I didn't tell you, which is in light of this very complicated nonlinear transformation of the pi field, I have to convince you that d mu pi square is invariant, which is not obvious, right? You should plug this variation here and show that it's invariant. So this is an exercise that can be done actually, and I mean, I don't know a better way to do it, but just let me explain what is the logic, what happens here. So if we take a variation of this derivative, d mu pi divided by 1 plus pi square, we obtain a remarkable fact. The remarkable fact of this covariant derivative is that it will be dependent on a term which is pi vector epsilon, which is this epsilon, vector d mu pi itself, plus something that sums up to 0 because of this denominator. Now, look at what happens here. So here you see this this object, it's orthogonal to d mu pi, right? And this object here, it would turn out to be parallel. So a general variation of this covariant derivative will be something that is orthogonal to d mu pi, and the part orthogonal, it's automatically invariant, because when you take d mu pi times d mu pi, we get a variation which is something orthogonal to d mu pi that gives me 0. So this d mu pi square is invariant. But a longitudinal part to d mu pi, it would basically not realize the symmetry. And actually, you can play this game, which I will not do, but it's possible to play the game in which you say that I have a delta with an f, a generic function of pi square, and I will have d mu pi here, of course. And you might demand what kind of f leaves this, makes this variation just orthogonal to d mu pi. And this would be a way to find the class of function f that makes the job. So 1 over 1 plus pi square, I want to stress that it's just one of all possible choices, because we have field definition, so we can do any sort of nonlinear transformation here and express these fields in many different ways. But the important point is that this covariant derivative is designed in such a way that its variation is orthogonal to the covariant derivative itself. So this is the important consistency condition to derive this covariant derivative. Okay, so now before the break, let me just sketch another approach, which is the reverse approach. So this basically, we started from a very simple model, and we performed a series of transformations to argue that indeed the most general Lagrangian compatible with this non-linearly realized symmetry is written in terms of this covariant derivative. So this is what we show. And this covariant derivative makes things invariant. So we are still invariant and so forth. Now there is a different approach that one can take, which is, let me start very generally with the algebra. Can I get to the same expression? And this is what actually Weinberg did in another paper, which I will not discuss. I will just show you what is the, I will just review what is the idea, which I think it's very nice. Yeah. Ah, very good, very good. No, I didn't write it down, but yeah, what I would identify the maximum value of this field sigma as psi bar psi in the UV. So this is what I would like to identify. Yeah. Yeah. No, 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 no. No. I started with the effective field theory at low energy. But that's, for instance, so this is the old way to derive these things, which is very, down to earth. We construct the effective field theory. But of course, like the way people construct effective field theories, let's say, more efficiently, is really to start from the the genetic function to the quantum effective action. So you couple two sources, which are the currents and so on, and then you derive word identities. And then you match the word identities with some effective field theory. So like people have some systematic way to do this computation. That's what you are saying, that you want to derive some relations and match the IR with the UV. But this takes more time. I don't have enough time, but thanks for the question. Yeah. Yeah. Exactly. Yeah, but such term would, so it's something that it comes at higher derivative, so I still didn't get there. But of course, such term would, for instance, give you some 5-point function between pions that will be really depend on will be sent to number of colors, right? Which is this West-Zumino term. Yeah. Okay, so before writing the effective Lagrange and do some computation, let me discuss this reverse approach, which I think it's very instructive. So in this reverse approach, you can ask the most general question. XA, XB from the algebra, we know that it gives, I erased it. Well, it gives just T. So this will just give me T that acts on pi, which gives me again pi. So this term is simple in terms of algebra. These are more complicated because this generator, when acts on the pion field, it gives me this function f, this function here. And then when I act again with this generator, I will get the infinitesimal transformation of these functions, will get a derivative. I will get an f prime. Well, f prime and g prime and so on. So actually this Jacobi identity gives a differential equation for the function f and g, and the most general solution is given by g, which is 1 plus 2 times f prime. So here I'm not giving you the detail by purpose, because I just want to explain you the logic of this computation. Okay, so it's like it's in this paper by Weinberg that I can give you. So f prime pi square f pi square divided by f pi square minus 2 pi square f prime pi square. And this is the most general solution. So you see, this function g is determined in this way, and then f, it's our choice. So we can choose any f, and this will close the algebra. And this reflects the fact that we have a field redefinition. Okay, we can also redefine the field, that we have a lot of freedom in this formalism. And you can play the same game for the covariant derivative. So you can play the same game, asking, for instance, that the action of this chiral current here on the covariant derivative, it's given by some vector VAB, which depends on pi, and epsilon BCD d mu pi d plus 0. So if I just ask that the action of this broken generator on the covariant derivative is orthogonal to the covariant derivative itself with some unknown coefficient, and actually it fixes me this function, the closure of the algebra. So I can fix this function also. This I can fix. And then I will get an expression which is very long, and I should have written it before. So, but I will not write it. I will just say the following, that you can derive a very general expression for the covariant derivative so just schematically, solving this consistency relation, we get d mu pi, which is again derivative of pi divided, I will just write one term, f squared plus pi squared, and then there will be another term, some factor, and then something which is proportional to f prime minus some other function of f and pi. So there will be like a very complicated relation, like this. And then you can choose any f, and this would give you like a good covariant derivative that realizes nonlinear lead symmetry. And the choice that gives the effective Lagrangian that I raised before, so the choice that gives us the Lagrangian that we derived with the linear sigma approach, linear sigma model approach, is just f equal to 1 minus pi squared divided by 2. Okay, so this was the choice that we made at the beginning. So you see, you could basically just require consistency of the algebra by assuming that one set of generator acts non-linearly, and derive a very general expression that is always true, and make, you could construct Lagrangian in terms of d mu pi, and this would be a very good effective Lagrangian. But then there are some choice of f that, for instance, make this term vanish. So the way you derive f is that you require that f prime minus some known function is equal to 0, so you can derive f. So for this special choice that makes this term vanish, we get very nice simple covariant derivative. And that's what we derived before. Okay, so now we are finally basically to the point in which we can write this effective Lagrangian and start to make computations and make predictions. Okay, so we convinced ourselves this covariant derivative is the object that makes this Lagrangian invariant under this SO4 symmetry realized non-linearly. So we can now construct terms. Like we can start to construct terms here and put 4 derivatives. Then there will be some other coupling, G42, which depends on d mu pi, d mu pi. It's like some different contraction of the Lorentz indices. Square plus dot dot dot. And well, we have to convince ourselves that this is a good expansion, right? That not all terms contribute at the same order. So the first thing to notice, of course, is that these things looks like d pi squared, and then there is some denominator, and the denominator, if you expand for small pi, it gives you powers of pi to the 2n. So any interaction vertex that you derive from this Lagrangian, it will have at least 2 derivatives. Okay, this is like the first basic observation. So in particular, let's consider a diagram. Let's consider a diagram like this one, which we have 4 particles in the middle, and then we attach derivatives here and here. We can attach derivatives here and here, I don't know. At least 2. And let's count what is the dimension in energy of this diagram. Okay? So what will be the dimension of this diagram? So there will be energy to what? So loops contribute with a factor 4, because we are in 4 dimension. Then there will be propagators. Propagators count with minus 2 units of dimension, number of propagators I. And then there will be plus these vertices. So there will be sum over the vertices of vi times the number of derivatives that we attach to each vertex. So this is the basic computation. So for instance, for this diagram, we'll have 12, then here we'll have 4 propagators, minus 8, then we have 2 vertex, 2 derivatives, plus 4. So in total, the dimension is energy to the 8 for this diagram. Okay, but now there is this minus sign that I don't like, and then there is a very simple relation, right, which is true for any diagram you can check, which is that loops is equal number of propagators minus number of vertices plus 1. And if I use this very simple relation, then this relation becomes energy to the 2 times loop plus 2, if I'm not mistaken, sum over I, vi, and then there is di minus 2. So this is nicer because this shows what? That, well, number of loop is positive. Derivatives, we always have more than 2 derivatives, so this is always positive. And this relation, it shows that if you compute in perturbation theory any diagram, the more loops you add, and the more derivatives you add, and the more suppressed is this term. And this, it justifies you the expansion of this Lagrangian in powers of energy, right? Because you are at low energy, E is small, and the more loop we add, the more vertices we add, the more suppressed is the diagram. Okay, so just a theorem. Now, let's see what kind of interactions we can have, right? So let's imagine to do computation at the leading order. So at the leading order, here we have 4 derivatives, too much. We have 2 derivatives. This is the least we can do. And we want to go to 0 loop, so we do a 3-level computation. Okay, so the leading order, it will really be given by G2 times d pi squared. And then let's say that we want to compute a 4-point function. We will have pi squared. Okay, so this is like 3 level, at 3 level. So this will be at 3 level, at 3 level. Now, what about the subleading order? And this is, sorry, this is dimension energy squared, because there are 2 derivatives. Now, what about the subleading order? So the subleading order, we can take, for instance, a loop diagram made of these guys. So if we plug here loop equal to 1, so we have 2 plus 2. Here we have 2 derivatives only, so this is 0, 2 plus 2 is 4, so energy to the 4. So we can take G2 interaction at 1 loop. This will be at order energy to the 4. But then we can also take these interactions because they have 4 derivatives at 3 level. So we can also add this G41 and G42 operator at 3 level. And they will all be of order e to the 4. And then you can go on. And then you see that this expansion, it mixes 3 level with loops. Question? Oh. I saw you were. Okay. So it mixes the level with loops, but the only important thing is that they have the same order in energy. So energy squared, energy to the 4. Okay. Another observation that we can make is that at the leading order, of course, if we add more legs, so let's say we'll have like processes which look G2, 2 pi squared, let's say, pi to the 4. And this would generate a 6-point amplitude. So this would generate a vertex of this form where the coupling it's still G2. And now let's imagine that I take double soft limit. So I send 2 pions to be soft. And then this will become a 4-point amplitude, which also has to have coupling G2. So you see, all these soft theorems, where we can imagine that we send 2 legs soft, and this 6-point function becomes a 4-point function, and so on, are consistent, because this vertex, when I expand, it gives me 4 particle interaction, 6 particle interaction with the same coefficients. So we see that this packages all this nonlinear relation between Feynman diagrams, this Lagrange. So okay, this is just an observation. Now let's do an actual computation. So let's compute, let's start at the answer. So this I can erase, it's just a simple power counting. So let's really compute now a scattering amplitude. So imagine that we have A, B, C, D, and I have 1 pion here with flavor A, B, that goes to C and D. And what will be the answer of that leading ordered level computation? Okay? So it's a vertex d pi square, where the flavor indexes are contracted. So we can imagine that if I have some labels A, B, C, and D, I have to contract flavor indices. So let's imagine that I contract A and B in this way, and C and D in this way. And then we have the derivative that follows the line of the flavor indices. So the derivative will basically contract, in this example, let's say in this diagram, A and B. Okay, so this will be basically a delta function, delta AB, delta CD, and it will only depend on the S-channel energy because the derivative acts on the particle A and B. And the variable S, let me remind you, it's just defined as minus PA plus PB, where PA and PB are the moment of this particle, you know, PA, PB, PC, PB. So we expect this computation at level just gives a bunch of delta function times S. So let me write it here. So we will have delta AB, delta CD times S. And then you can imagine what happens, because I can do T a new channel, and then I will get T instead of S. And I will contract the indices in the T channel, so AC delta BD. Then I will have U delta AD delta BC. And this will be the answer. So this is like the amplitude at 3 levels. Now, this amplitude has some nice symmetry properties, because you see, S, you can think of it as a function, generic function of S, which is symmetric in T and U, because T and U are not present. And then this, you can imagine it's like a generic function of T, of S and U, and same thing for U. So actually, in general, you will parameterize this amplitude, you can parameterize this amplitude in terms of function, which are these color ordered functions, A of S, T and U, which is symmetric in T and U, and these are the building blocks. Okay? Now, imagine that I didn't do this computation, and I just told you that at 3 level, you want an answer which is which has energy square in dimension, and it's only symmetric in T and U, let's say. So what you would write? You would write S, then you could write T plus U, but T plus U it's just minus S because of momentum conservation, and that's it. So you see, the answer that you get at 3 level, it's the most general structure that you can get compatible with all the symmetries. So like crossing symmetry, analyticity, polynomial boundedness, it's just S. You're done. And this is basically the content of effective field theory. So all these things that we did, so all the answers we get from the effective field theory, we could guess it if we knew the rules of the game. And just write the interactions that are compatible with these symmetries. Okay? Okay. And another thing is that this answer, which we derived basically immediately, it already contains the pion-Soft theorem. So if we knew this answer, we didn't need to derive the pion-Soft theorem using current algebra, taking momentum soft and so on, because you can just imagine that you parameterize t with scattering angle. So t is just minus s divided by 2, 1 minus cos theta, and u, it's minus s over 2, 1 plus cos theta. So this is my way to parameterize T and U in terms of physical momenta, which depends only on the energy in the center of mass and the scattering angle. And if I parameterize in this way, you see that if I send S to 0, this full amplitude vanishes. And this is the pion-Soft theorem. So if I take physical momenta and I send one momenta to 0, like the one in the S channel, let's say, I get 0. Okay? Pion-Soft theorem. Now, let me go to one loop. So, well, to one loop. Let me go to subleading order. So let's go to subleading order. So this actually I need, because it's a bit long, I need to write it. So at the subleading order, we have to do now a loop computation. So we really have to compute something like this, where we have the momenta somewhere. And then this would be from this interaction here at one loop, and then there would be diagrams that comes from this contact interaction, like this, with some different vertices. So this will be G2 squared, and this will be G for 1 or G for 2. And we can do this computation. So we can do this computation. And let me write just one of these partial components. So let me just write A, S, T, and U. So it will be given, of course, by delta AB, delta CD, and then I will have a G2 squared times minus over 2 pi squared. So, okay, it's a bit long. I should have written it before. But okay. S squared log of minus S. Then there will be minus 1 over 12 pi squared U squared minus S squared minus T squared log of minus T. The same thing with the U and T exchanged. T squared minus U squared log of minus U. And then there will be, of course, a divergence, because now we have divergences. We're at one loop. Squared plus T squared plus U squared. And here we have log of lambda squared. And then we have minus 1/2 G for 1. So these are the three-level computation that comes from these vertices with four derivative. So it will be either S squared or T squared plus U squared. It's the only thing with the four derivatives that we are writing, which is symmetric in T and U. So minus 1/2, 1/4 actually, G for 2, T squared plus U squared. Here there is a parenthesis. Okay, so this is the result. But now, this result is still not very nice, right? Because we have a divergence, we have like a log of lambda squared. So what we can do is that we can reabsorb this log into this constant, because they're just the bare couplings at tree level. I mean, the bare couplings with tree level insertion of this operator. So we can just redefine them. So imagine that I measure G for 1 at some energy. So I perform some experiments at energy equals to mu. And I reabsorb the bare coupling and the divergence into these quantities here. So this I can define it as G for 1 minus 4 over 3 pi square log of lambda squared divided by mu squared. Then G for 2 mu, which is G for 2 minus 2, okay, squared, log of lambda square divided by mu square. So with these two measurements, I can redefine G for 1, G for 2 in terms of this G for 1, G for 2 at the scale mu, where I do measurements, and I can write this expression in a more physical form, where here there is mu, here there is mu, here there is no more divergence, so like a finite answer. And of course, the logs now makes more sense because they have to be dimensionless argument. I can put mu square, mu square, mu square. And that's it. Now, this is the answer that you get at one loop, and it's the most general answer. It's also compatible with all the symmetries of these interactions. And you see that now this is predictable because once I measured these coefficients at the scale mu, and I plug it here, the scale mu is some scale that I chose to do the measurement, and then this, it makes me prediction for the amplitude. Okay? And then you can go. So this is an example of order S to the 4 computation. Any questions so far? It's the same thing. Yeah, exactly.
But you know that normally it works good for absolutely free theory. So this is what you can all kind of derivatives. Like yeah. What's the predictive power? Because like okay, you do the computation, but then you have to fix as many.
Yeah, of course.
So basically it's not predictive power.
Well, the predictive power is that you can, let's say, with two measurements, you can plot the function, meaning that you see.
But every coupling would be like relevant in some sense.
Yes, but no, that's true. But with that, you can go to higher and higher energies. But if you are interested in a computation which is only valid up to some energy, where you can forget about these higher order couplings, which will contain more derivatives, therefore will be more suppressed, I only need the finite number of measurements.
Right. So you're saying that just powers of S and 4
Yeah. Will suppress. Exactly. Well, yeah, exactly. I mean, the physical answer will not know about these divergences. I mean, that's just an artifact of the perturbative computation. In the end, the answer is finite and higher order interactions suppressed by more powers of energy. So when I say predict, I just say that, you know, if I'm interested in energy which are S, let's say, smaller than, I don't know, 500 MeV squared, I can plot this function maybe and compare with the experiment and it matches. Then I'm happy. And I needed only 3 numbers to do it. So, yeah. While with QCD, you need to do some lattice simulation and it's much more complicated. Yeah. Okay. Sorry? Counter terms.
In a sense, quantum is like something more like what I was told symmetrical.
So basically this, so the answer was, I mean, the question was about the counters, and the answer was just that these couplings, they act as counter terms. You can just reabsorb divergences in the definition of those couplings.
Another thing that is maybe some gap now regulate the terminal, you try to just get rid of some gap factor.
Yeah. I mean, this lambda, it's really a physical cutoff, right? I don't care about what happens above the scale lambda. I just absorb it into a definition of these couplings. Yeah. Okay. So maybe the last comment I want to make. So there are two last comments, and then we can finish. So the first comment is that these logs come from a direct computation, right? So I do Feynman integrals, I compute them, I see these logs, I stare at them, and I'm happy. But then I also told you that the most general answer that you get, it has to be compatible with the principles of unitarity, crossing symmetry, analyticity, and so on. So actually, an answer like this can be derived without doing any computation, without even doing any Lagrange. So what I will... Yeah, the answer for the scattering amplitude can be derived without doing any computation, because it's compatible with the symmetry principle, should follow directly from the symmetry principle. So, and to do this, maybe let me simplify it a little bit, because here we have flavor, so it's we have vectors, and it's a little bit more complicated. But let me just simplify the setup and only explain you the logic, and then one can work out the details for this case. Okay, so just a comment. So imagine that instead of having this complicated Lagrangian, we have something more simple, which is an effective Lagrangian, like d phi to the 4. Well, d phi squared plus d phi to the 4. And this, when you expand, it generates, well, this is just like a scalar field, there are no indices. This just generates interaction like d phi to the 4 plus d phi to the 6, and so on. Okay, so it's like a little bit simpler than the pions. And now let's try to use the same principles of knowing the answer at 3 level, the dimension, okay? So this vertex is like 4 derivatives, so it should be energy to the 4. So I expect that any 3 level computation, it will give me something of order s squared in the Mandelstam variables. And since I have only one scalar, now I have full crossing symmetry, and at 3 level, this answer should only give me something like s squared plus t squared plus u squared. That's the only thing that can give me. So if I call this coefficient C4, this should be C4. And this would be the answer without doing any computation. Now, what about the loops? So to guess the loops, well, there is the, let's say, the polynomial part of the loop answer, it's easy to guess, because now we just have to think what are the polynomial of degree, well, of degree 3. So here there will be STU. So there will be some C6 STU. This is something I can write, and then I can write also C8, which is S squared plus T squared plus U squared squared, plus dot dot dot. So this would be energy to the 4, energy to the 6, energy to the 8. This is like the general answer I will get from the effective computation. But then at some point, I also have to add loops, like we did here. And in this simpler case, loops just enter at order e to the 8. So now we want to guess loops. And to guess loops, the simpler thing to do is just to use unitarity. And unitarity, of course, it's the statement that the way we take a loop diagram and we cut it, we get the square of the 3 level. And then you see immediately that from this expression, the 3 level is order S squared. Therefore, when I square it, I should get something of order s to the 4. And from the unitarity equation, written grammatically, we know that this s to the 4, it has to be the discontinuity of the loop amplitude when we have the diagram. But what is the function that has a constant discontinuity? You know? So the question is like, what is a function that has a constant discontinuity? Yeah, log. Yeah, it's log. So here the only thing I'm saying is that you want a function that whose discontinuity is just s to the 4. So I mean s to the 4 times a constant. Basically, the function is the log. So the only thing that you can write is log of minus s, and then log they don't want dimensionful arguments, so I put divided by mu square. I make it dimensionless. So you see, immediately from unitarity, you see that the most general answer that you will get because of unitarity will be like s to the 4 log of minus s divided by mu square. That's how the log arises in perturbation theory. It's just a consequence of unitarity. And this can be made precise in the sense that if you write the correct factors in front here, and and remind that the discontinuity of the log is minus I pi. Okay, so there is also a factor pi, there will be factor pi around. You get, and if you do it for this case of flavor, which is a bit more complicated than this, you will get exactly all these factors without doing any computation. So, and this is why, I mean, this like reflects the statement that the answer that we get from effective field theory is compatible with all the symmetry principles. So this was comment number 1. And this maybe I will discuss in the last lecture. Let's see. Then comment number 2 is that actually, yeah. It's very simple. It's that unitarity. So I can do it. I can write it more precisely, but let me state it vaguely. So unitarity tells you that the discontinuity of the loop function has to be equal to the square of the tree level. So the square of tree level, it's just s to the 4 times a constant. So then, to know the full answer, you want to know what is the function that's like a constant discontinuity. And that's the log function. Then you get log of minus s divided by mu square. And these are exactly these logs that appear here. And then if you do the computation precise, you put the proper pi factors and the proper factors here, you get also the precise coefficients without any computation. Okay. And then the second comment I want to make is another beautiful observation, I think, which is that these logs are also natural from renormalization group arguments. So what I mean by renormalization group arguments, you see, this mu here, it's a little bit arbitrary, right? I said I go to some energy mu, I perform some computation, I perform some measurement, I measure G41 and G42 at the scale mu, but then what happens if I change scale mu, if I do measurement at some other scale? Will the answer be different? And the answer is no, because actually this function, it has also the property that if we take the derivative mu d in d mu, this is equal to 0. And this is another way to actually derive this expression. So let me, okay, in the last 5 minutes, let me just make this comment. So it's like a third derivation of this one loop answer. Let me just sketch it. So what I mean by RG group methods. RG methods. Okay. So I mean the following. I mean that I take the amplitude now and I fix the angle, so as I did before. So I really take the the pion amplitude. Well, here I'm taking the A. So A, which is only function of energy, where I define S, the Mandelstam S, to be 4 times the energy squared, and then T is minus S divided by 2, I write it again, 1 minus cos theta, and U is minus S divided by 2, 1 plus cos theta. So I fix angle, and then everything is just a function of energy, so there is only one variable here. So I write this function as some coefficient C2, energy squared, and then there will be some energy to the 4. I put S2 square here. Then there will be a function, which is this loop function that only depends on dimensionless variables, right? This is like a transcendental function. So it will be a function of energy divided by some scale mu, plus sum over n, and there will be some these local interactions here, this G41, G42, that now I call C4, following Weinberg. So here we get like G4 and at the scale mu plus dot dot dot. And now what you want to require is that when you perform a computation the scale mu and then you change scale, the answer is invariant. So you want that if I take derivative of mu d in the mu of this expression, this has to be equal to 0. Okay? Now let's do it. So what happens? If I take mu d in the mu, the first term doesn't count, so we take derivative here. I did it at home, so this gives minus e divided by mu f prime e divided by mu. Then there will be plus sum over n, c for n, and then there will be basically the beta functions for this interaction here. They call G4N, like this. And this has to be equal to 0. Now, this has to be true for any angle, okay, for any energy. So in particular, for this to be 0, one simple condition that one can impose is that this derivative, it's just a constant. So it's some constant. Because you want this expression to be valid for any angle and any energy. So the simplest thing is that we take the derivative with respect to mu, it gives a constant. And then we have a simple equation, differential equation of the form e divided by mu times f prime e divided by mu is equal to sum over n of some constant b for n. And now if you solve this equation, it's a differential equation, right? The only solution of this equation is like log, right? It's like e over mu over e on the other side. So f over e over mu has to be equal to f0 plus logs. Sum over n of c for n, there will be this b for n, and then there will be log of e divided by mu.
Sounds like something that you could just extend to further terms.
Yeah, if you do it, exactly, if you do it, you get a prediction in the sense that you get, for instance, at the next door, that you get log square from this method. And if you do the computation from the ambient point of view, you get also log square. And then you can also fix the coefficient, but this method does not fix the coefficient. To fix the coefficient, this b for n, right, this how the couplings run, then we need like some information, right? So this we fix them, for instance, looking at this step. But the structure is exactly the same. So
I mean, this is like, you basically saying that you are.
no, at leading order. I mean, this, you know, I'm working at, so you see here there is dot, dot, dot. I'm working at order by order in perturbation theory. So of course, like if I go at higher orders, here we'll get terms that also contain function g for n. Yeah, so I'm just saying that you see g for n at one loop, mu is basically this thing. It contains log of lambda squared divided by mu squared, but then if I do this computation at higher loops, I'll get log square and so on.
It's also strange, right? Because normally we usual beta functions they are always perturbative.
Yeah.
So it starts with mu g is some g squared, g cube, etc. And yours the function starts with constant. This is unusual, right? Normally you have log, but in front of log you also have counting constant because on real level you don't have any log, right?
Let me see. So you say you want, for instance, you have in mind.
Yeah, for example, beta function for QCDs, it's whatever, some number of labels, GQ, etc.
No, I understand what you mean, but this is a much simpler statement. I'm not, you see, I'm not saying how this function varies with the coupling. I'm only interested in the dependence on this,
Yeah, but what I'm saying is that coefficient can be functions of coupling. And normally they are the functions. I don't know if the functions are very
I know what you mean, but here, let's see, what I want to say by this. So let me look, let me look at I haven't thought about this, good point. Look at the answer. Because you see, the answer at the leading order, it's really just given by some constant b for n.
Yeah, so this is
Log
like it's true, just with
mu divided by mu 0,
Yeah.
and that's it. Now you see, I haven't. Okay. To be, I only studied this argument on this example, but I don't know. Like if I change the example, if it gets more complicated. In this case, the equation is pretty simple because the answer is simple, and the simplest answer is this one, let's say. But I agree with you that maybe if I do the scattering of, at one loop QCD, it will get more complicated terms, and you should start to see more complicated stuff. I don't know, but it's a good point, yeah. I would stick with this example. This is what you get, because it's very simple. Okay, and okay, I think I will stop here. This was like more than enough about logs. Like, too many ways to derive logs. Okay.